Now we'll continue with results from Qualify. Franz BORMANN will present the validated models of adhesively bonded composite-to-metal joints. Franz, would you like to introduce yourself?
In the upcoming presentation, you will see the recording of the work that I've been doing within this project.
Hello, everyone. Within the next few minutes, I want to present you the technical work that has been done with M2i in the framework of the Qualify project. We developed models and methodologies that help us to get towards the prediction of the lifetime of hybrid structures. In the Qualify project, we considered two different joints, which is on the one hand, the Dahmen group joint, and on the other hand, the BORMANN system joint. They are kind of similar, but still very different to each other. In the Dahmen group joint, we have here a U-shaped steel part where we have then a thick adhesive that is glued to a composite panel that you see, actually don't see here on the other side. Separated between them, you have balsa, and on the bottom, you have some foam also for some separation. The BORMANN system joint has a relatively thin adhesive that connects the steel to the composite. And here you have a hardwood wedge and a balsa, again, as a separator. So what can be done is easy. You can take a ship, you can simulate it under environmental conditions and operating conditions. Then you can also create a model, which is the three-hole model with some representation of the U-joint here of the joint that we consider in the project, for example, in the Dahmen case. And then this representation can be used in order to simulate the stresses, to get insight into the local stress distribution. However, we cannot at this point say yet if this design will fail or if it's safe to employ. So we need actually some design validation criteria in order to assess the strength of this joint and the safety of it. So for that, within M2i, we developed actually a high fidelity model approach, which is based on the large scale samples, as has been also experimentally tested. And then using those high fidelity model, we use a methodology to create low fidelity models out of them that actually are representative for the design validation model. Using then a transfer methodology, we can get insight into the safety of the joint. How did we actually pursue the whole modeling approach? We started with a material level and with a structural level. For that, we considered experiments, and we used those experiments to calibrate the material models and the constitutive models that are required for our high fidelity models you see on the top. And we need to calibrate for the steel, for the adhesive. We need to look into the interfaces, composites, etc., etc. And then in the end, we do the component level tests in order to validate our models that we have calibrated. Now let's have a look at the first results for the Dahmen joint, for example. There we have here on the left-hand side the tensile test. Here again, you see the tensile specimen. And on the bottom, you see a video of the tensile specimen being loaded, where you see the stress distribution in the joint until the final rupture of the interface or the skin failure that we simulated. On the top side here, you see the force displacement curve in comparison experiments versus simulation. As you see, the behavior is relatively captured relatively well, slightly underpredicted due to a conservative modeling approach. For the displacements, it's to be noted that we considered 2 points here in the specimen for one simple reason. In experiments, you have so many phenomena that are included into the clamping, some slippage, some mesh stiffness, that we don't want to simulate with FEM, it takes too much time. So we just looked at the virtual extensometer results here. It's a good agreement. And the same good agreement has also been achieved with the Arkin test you see on the right-hand side. And we then did a virtual extensometer test, relative displacements between those 2 points to get the force displacement curve. Damage was not included in those modeling approaches for the simple reason that it was high complexity. We observed some yielding of the flange here. We observed yielding of the adhesive way before actually the whole joint failed. So at the moment, we still didn't look into the failure. That's still under investigation. Yet, relatively good agreement that we have achieved here. Then we are now at the high fidelity models. We created the high fidelity models. What we do with that one is we extract the load at failure initiation. In the current approach, we consider large-scale yielding of the adhesive or the steel as failure initiation. We can consider damage of the interface or the composite failure initiation criteria. We look when does the first criterion take effect, and then we track the load for that one. We save the load. We note the load, the failure load. Then from the high fidelity model, we create a low fidelity model through sub-model simplifications, such as the geometry. As you see, the flange is very simplified, represented here. We simplify the mesh, it's coarse mesh, it is simple elements, and we simplify the material behavior. We don't have complex material behavior anymore, such as yielding, nonlinear behavior, fracture. That's not of interest, because at the point where the failure initiates, none of these effects has taken place yet, so we can discard them, such as has been done in the design validation model, such that the low fidelity model now matches the design validation model in terms of mesh, geometry, and material behavior. Then as a next step, we take the failure load that we extracted from the high fidelity model and we apply it to the low fidelity model. Then comparing the stresses that we have in the design validation model and the stresses that we have now observed for the low fidelity model as a representative for the failure load, we then can compare those two stress states and evaluate the safety of the proposed design. We can use also the high fidelity model and the low fidelity model for one more thing. And that is the creation and definition of the fatigue spectrum for the fatigue test, as has been done in the project. This is the fatigue spectrum here that has been needed in order to perform the fatigue analysis and fatigue tests by Juchent. Similar approach can be also taken by the BOE joint. As an example, I want to show here some preliminary results we got for the joint. As you can see here on the right-hand side, force displacement curve, again, I chose 2 points here with the relative displacement, and the results of the simulations, they match the experiments relatively well. Once we also now include interface failure with an accurately calibrated interface model, we will be able to capture the failure initiation of that joint as well, such has been predicted here. And then further on, we again create a low fidelity model and use that one, design validation model, to assess the safety of the joint. Now, what did we learn about the joints? What we learned about the Dahmen joint design is that the bulk adhesive is very unlikely to break under different loading conditions. It didn't break at all. But the failure always initiated with the yielding of the bulk adhesive. So first the bulk started to yield, and then at some point we had failure of the interface here, of the composites here. And the ultimate failure is likely to happen near the interface adhesive to composite, so in this area, especially in the presence of high pure stresses. What we learned of the BOE joint design, the critical load area is the steel hardwood wedge transition zone, so that area here. And preliminary tests, they indicated that the failure initiation started or took place already before the first vessel drop in the experiments. So that means we have already a failure initiation without any loss of joint stiffness, joint integrity. Now to sum up, high fidelity models and low fidelity models. The high fidelity models enable, once they are well calibrated, a detailed insight into the failure mechanism itself and into the load at failure. It is useful for studying alternative material combinations, and it is easy to extend to prior damage and also age conditions. The low fidelity model, further on, is easy to implement. It is an efficient tool for the design validation of different kinds of joints. It's an efficient tool for the definition of the fatigue spectrum. And on top of it, similar to the high fidelity model, it can be combined with the influence of prior damage and an age condition. Altogether, high fidelity models and low fidelity models, they are very valuable tools for studying and evaluating almost any joint design. With that, I want to thank you for your attention. And if you have any questions, feel free to ask them. I'll do my best to answer them. Thank you.
Thank you, Franz. It's very nice. Are there any questions from the floor or maybe online? Yes, please.
I maybe have a question, yeah. Thank you for a very insightful presentation in multi-fidelity modeling. I was wondering, in one of the first slides, you showed the results for the tension test, and I think I saw a load drop there for the model, but you said you did not model any failure mechanisms. So what is causing this drop in the load?
So basically, I actually, for the tensile test, I modeled the damage, but for the Archon test, not. It was just a slippage of word in the pre-recording.
Okay.
So
yeah.
my apologies for that one.
But then the question is, yeah, what kind of failure mechanism is occurring and where?
So what we calibrated for was the skin failure of the composite. The interface model was calibrated with DCB tests, double cantilever beam tests, where then the fracture energy was recorded in order to propagate the pre-crack in the DCB test. That energy was then used for a cohesive zone model, that is an interface model that was plugged in between the composite to adhesive interface. And there we used the fracture energy as an indicator for the fracture initiation and fracture propagation of that one.
Okay, and that caused a bit too early failure in the end?
It because if you want to really intricately model the failure of that joint, you have to consider you have two mechanisms. On the one hand, you have the opening normal to the interface. On the other hand, you have also the shearing failure. Now, with the DCB tests, they get only the normal opening test, energy. Then for that model in general, you need the energy that is required for the normal opening. You need the energy, if it's differently, also for the shearing mode.
Yeah.
And on top of that, you also need then the stresses that are required. So for example, sometimes you have 20 megapascal and then something breaks. That's the critical stress that is plugged into that model. With the DCB test, you cannot get it directly by measurements. It's in the end some calibration. And that is always prone to some estimates. Yet, the most crucial thing that we did not have access to at the time we modeled that one was the shearing behavior of that one. And that is because the composite to adhesive interface is very hard to model the shear fracture, shear failure. You need to have dedicated experiments for that one as well. That's also written in the guidelines by Bureau Veritas and Lloyd's Register. So you find there actually what that helped us actually to draft the requirements for the guidelines.
Mm-hmm.
What do you need to calibrate? What tests do you need for that?
But those tests for the shear failure, they have not been performed in the project?
They have not been performed
so they're still
for
needed,
that specific interface.
Okay, yeah. Now clear? Yeah, very clear answer, thank you. Yeah.
Thank you. Franz, maybe I'm not sure if this is related, but there is a question. How do we include damage into the reliability assessment?
So damage has been included in some modeling. It was done while the recording of the presentation was taking place. Results were not there yet. How it is included is in collaboration with Bureau Veritas, we came up with this approach that damage, if it nucleates at the free interface of the diamond joint, for example, if it nucleates at the free interface, it's visible quite early, at an early stage, so we don't need to, and it's not that severe. The most severe case that we can consider is that the damage nucleates on the interface on the side that is hidden from the blank eye, so where it's connected to the foam part. If damage nucleates there, then it grows throughout the process until it is either inspected or found by the inspection after those 5 years, or after it's visible with a blank eye. And for that we assumed, the idea came from Bureau Veritas, that we just assume a circular propagation. So a half circle that nucleates or starts from the bottom of the joint going up to the free surface, and that means that you have a radius that is equal to the bond length. Now we assume that one, we assume then a representative of the real joint, where we have a long flange as it is also in the real life application, and we assume stresses that are similar to the real operating conditions, apply them in the numerical model, and we see then if a damage that is of a radius, half radius shape, if that propagates or doesn't propagate under the operating conditions. If it does not operate, we want to know when does it propagate, so we increase the load until we see propagation of the crack, until the final failure. So then we have multiple steps. One of them is where the crack propagates already, where it starts to open up from a half circle to more like a rectangular crack. And then you have a reduction in in the bond area. And with that one, you have also a reduction in joint strength. And based on that one, we then can calculate also with the modeling, when does the ultimate failure happen, and what is the reduction factor in bond strength, joint strength at all, in total.
Great, thank you. There is one question from online, right? Is there any report available for observers on this topic? So I assume they asked that. And you are doing deliverable 161. So obviously, all deliverables will be available in the outputs library of the Interact2Sys website. And they will be delivered with the closure report, and this will be done in January. But we will also, please, contact me, and I will deliver whatever reports you are interested in. Okay, great. Thank you, Franz. Thank you very much.